This is Algebra 2 with Trig 6.2. We're looking at some properties of exponents. We've been through this a couple times already this year. When we're multiplying the same base, we add exponents. Here, when you're raising a monomial to a power, this you can distribute in because there's no plus or minus in between your variables. In this case here, when the bases are the same, you would subtract exponents. Here, when you have a base with a power and you're raising it to another power, you multiply exponents. If you have a negative exponent, what does a negative do? Puts it into the denominator. And if you have this quantity raised to a power, again, you can distribute that in. And of course, all of these can work the other direction also. If you have the same exponent, then you can pull it to the outside. You can break up factors any way that you want to set up your exponentials. So some properties of the radicals is as long as you keep the index the same, you can separate into two radicals. Or if you're in division, you can break that into two radicals. Now remember, this would work both ways. If they're separated, you can bring them together as a single radical. You can write it as a single radical. So we look over here, and for this one, there is a cube of 125, and that's actually 5. Because if you take 125 and you write it into 3 equal pieces, 5 times 5 times 5, and 2 times 2 times 2, we can take the cubed root of 125 and take the cubed root of 8. You're looking for 3 of a kind because it's the cube root. So that comes out to be 10. You would get the same thing if you multiply this together to get 1,000 and then took the cube root of 1,000. In this one, of course, there's not much you can do with it the way it is. So if we break this apart as the 5th root of 96 divided by 3, and we simplify that, now you can break 32 up, and 32 breaks up into 5 different 2's. 2 times 2 times 2 times 2 times 2. So the 5th root is considered 2. Now sometimes there's going to be other parts left over. So if you break the 104 apart into 52 times 2, break the 52 up into 26 times 2, break the 26 up into 13 times 2. Now we have 3 of a kind. That's what the cubed root means. So we pull that out, and we're left with a 13 inside. If you realize that 8 times 13 was 104, great for you. you could break it apart into 8 times 13 because 8 is a perfect cube. Remember, when working with these, you want to try to use perfect cubes. 1 is a perfect cube, but that doesn't break these apart much. 8, 27 is a perfect cube. 3 times 3 times 3. 4 times 4 times 4. 5 times 5 times 5. 6 times 6 times 6. Those would all be good numbers to be working with. So you look at the 48 and which one of these numbers goes into the 48. 6 times 8. Oh, I'm sorry. This is to the 4th power. It's no longer the 3rd power. So you need 4 of a kind. So you can just break it apart in any way that you see fit. 6 is broken apart as 3 times 2. 8 is broken apart as 2 times 2 times 2. So there's your 4 of a kind. And we didn't use the 3. So we're back to our perfect cubes. So does 8 go into that? 27, 64, 125, 216. And if you realize 216 looks like it's doubled for that. So 2 times 216. I wouldn't have realized that earlier, but if we look at it from this point of view, you can see that 200 and 200 is 400, 16 and 16 is 32, so it's 2 times that amount. When we made our list here, 2 cubed, 3 cubed, 4, 5, and 6 cubed. So this is 6 cubed. If you didn't recognize that, you could break it down all individually. There's 3 of a kind. Don't forget your index. A very common mistake to lose credit for is not including your index. You got to have the proper notation. Now, when we're collecting like terms, we've got to have like radicals. That means the index has to be exactly the same and the radicand has to be exactly the same. So these are the same, so essentially they're like x. We have 7x minus x. So it would be 7 minus 1, and then your x, or in this case, the 5th root of 12. The radicals don't fall off. It's not just 7. Consider those like variables. So 7x minus 1x is 6x. And your x value is the 5th root of 12. Here we notice that the index is the same, but the radicands are not the same. Since they're not the same, we have to see if it's possible for them to be the same. So let's break these down. You need to think about what makes 48. 16 times 3 makes 48. 25 times 3 makes 75. We know the square root of 16. We know the square root of 25. Now notice that the indexes are the same, the radicands are the same, so we have 4 root 3 plus 5 root 3 is 9 root 3. Here again, the indexes are the same, but the radicands are not. We have to see if we can get these radicands the same. So we want to simplify them. if you're not sure how to simplify them, just break them all the way down. 9 times 9, 3 times 3 times 3 times 3. So now we have the cubed root of all that. And then this can be broken down into 3 times 8. 8 can be broken down into 2 times 2 times 2. So 3 times 2 times 2 times 2. This is the cubed root, so we're looking for 3 of a kind. What do we have left inside that we didn't circle? We're looking for 3 of a kind. What do we have left inside that we didn't circle? And look at that. The indexes are the same, the radicans are the same. So 3 of these minus 2 of these gives us 1 of these. Cubed root of 3. Okay, let's take the fourth root of 405 and just start breaking that apart. I know that 5 goes into 40. I know that 5 goes into 5. So this is 5 times 81. On this side, you can break this one down any way that you want. I know that 10 times 8 makes 80. Well, 81 is made up of 3 times 3 times 3 times 3, so that's 3 to the 4th power. Maybe you like that notation. Ten is made up of 2 times 5, and of course 8 is made up of 2 times 2 times 2. So there's my 4 of a kind. So I'm going to say 2 times 3 with the 5 left inside. Here's my 4 of a kind. And look at that, the 5 is left inside. Now they both have the same index and the same radicand. This becomes 6 fourth root of 5 plus 2 the 4th root of 5, which adds together to be 8 the 4th root of 5. So what you want to work with is breaking these down any way that you see fit. Any way that you see that would be helpful. Another way we could have broken this one down is 16 times 5. We could have gotten there a little bit quicker. But whatever you see. On the opposite side, we're looking to keep simplifying. So we're looking at the 4th root. So we're looking for 4 of a kind. Well, I've learned that 625 is made up of 5s. So 5 times 5 is 25, times 5 is 125, times 5 is 625. And then the z's. You could write those all out if you want to be crazy. Now we're looking for groups of 4 of a kind. So there's 4 of a kind, so I have a 5. There's 4 of a kind, so I have a Z. There's 4, and there's 4. So notice that there's nothing left inside the radical, so we'd be all done. We've simplified it. On this side, we can break apart these. The more you work with them, the more familiar you're going to be. 32 is broken apart into a whole bunch of 2's. So we have 2 to the 5th power, m to the 5th power, and n to the 30th power. I'm definitely not going to draw 30 n's. Now, when you have a power on the outside, we can multiply that to all of the exponents. And when we do that, we can simplify. And there's our answer. Now we have the 6th root. There's nothing we can simplify inside here, so we're going to break it apart into 2 different radicals. We have 6 that are all the same. We have 6 that are all the same 3 different times. Alright, now this one gets a little weird. First of all, we're going to reduce the 8 and the 12. 4 goes into 8 twice. 4 goes into 12 3 times. Then we're going to work with the k's, where the k's have the same base, so we can subtract exponents. There's only one set of m's in here. And the d's have the same base, so we can subtract exponents. So when you subtract 2 minus 3 halves, that's like 4 halves minus 3 halves leaves you with 1 half. So that's k to the 1/2 power. And when you have 2/3 minus a -1, that's really like adding 1. So this becomes d to the 5/3. So we could possibly leave it in this format. Another format is to try to get all of the bases, all of these denominators the same. And if we were to do that, we'd look at this and say, what number does 2, does 5, and does 3 go into? And of course, the only number that they all go into is 30. So that would be a pretty far stretch. Now, you'll see us doing this occasionally if we want to group these all up and put them together. I'll just show you what that looks like. Here we would have, if we're going to make the denominator 30, we would have to multiply the top and the bottom by 15, top and the bottom by 6, top and the bottom by 10, so that's going to leave 2/3, and the cubed root, or it's not the cubed root, it's the 30th root. This is starting to become weird. The 30th root of k to the 15, m to the 12, and d to the 50. Well, I guess if we're going to do this, we could break this, you could bring out a whole 30 of them. So that's another way it could be written. That's not d to the 30th, that is the 30th root. So perhaps this would be a cleaner form to have left it in. But just wanted to show you that there are options and ways that you can represent simplification. So here we're going to take the 56 divided by 7, the a to the first power minus 5/6, the b to the 3/4, and the c, when we move it to the top, is going to have a positive exponent. So this is 6/6 minus 5/6. We'll just leave it in that form. This is x cubed times x. This is y cubed, and y cubed. And this is z cubed. So there are 14 z's, 9 y's, 4 x's, and then my 6. And 6 is broken down into 2 times 3, but there's not 3 of a kind. So I'm looking for any 3's of a kind. Here's an x. We have y 3 different times. We have z 4 times. Left inside, we still have the 6, we still have an x, and we still have a z squared. This might be a good method for you if you don't want to write them all out, all the x's, all the y's, all the z's. Here, there's not much that we can do with just the way this is written, so we're going to break it into 2 separate problems. We're looking for 4 of a kind. So you'd get x in there twice. 4 of a kind, you would get y in there 4 times. There'd be 2 groups of 4. There'd be 4 groups of 4. Now when you look at this, we have the cubed root of u. So we have 18 minus 11. Since the indexes are the same and the radicands are the same, we can just subtract. In this case, since the a to the 4th, b to the 2/3, a to the 4th, b to the 2/3, since those are the same, we just add our like terms. And in this case, we need to get the radicands the same. So we have 4 of a kind we're looking for. Well, we have 7 S's. We have 4 of them, and we have 3 more. On this side, we have our S. Now 16 can be broken down into, 80 can be broken down into 16 times 5. Well, there's not 4 of a kind in 5. There's 4 of a kind here. And we're left with 5s cubed. 16 is broken down into 2 times 2 times 2 times 2. So there's 4 2's in that. We're left with 5 and an s cubed. So look at what just happened. The indexes are the same. The 5's are the same. The s cubes are the same. The numbers on the outside are like terms. (10 minus 2 is 8, and our radicals are exactly the same, so we keep it all together.